Hi, my name's David Vizard and you are watching PowerTech 10. Give me a few minutes of your time and I will give you the benefit of my over 50 years of race-winning engine building. Hi, this is David Vizard. This is part 2 of our Edelbrock porting seminar, right? And what you're probably wanting to know was the mods that I described at the end of part 1 worthwhile doing. Did they pay off? Well, I'm just going to show you the end of part 1 and let you take it from there. Thank you. We're going to now see if this extra bias emanating either to or away from the center of the cylinder pays off. Did that move pay off? Well, you bet it did. Look at this. Increase our exhaust everywhere over the previous test. On the intake, same thing. But look, it dipped after that there. Maybe we still don't have enough bias. Let's just check that out. Here's the bias flow curves. We've moved everything up here, but look, it barely increases any more than it did before. So we need to give that some attention. Well, so far I've walked you through these port mods a small increment at a time. If we keep on like this, we're going to be on this for about 2 hours. So I'm going to jump a few steps here, but each of those steps follows the same routine as we've already done. I'm going to increase the bias slightly, increase the width of the port slightly right across the port, and look at a few other details such as the way on the intake, the way the air turns on the top of the port into the cylinder center side. If you look down the intake port of any small block Chevy, you will see that the intake port or the valve is in a flow shadow on that side. We've got to try and get that air to go around the side as easy as possible. So we're going to look at mods like that and see where that gets us, and I'll explain each step of the way how that goes. To do this part past the bowl here, we used a ball cutter, 1/2-inch ball cutter. Right, and that's about the width you need to do there. Now, this is a little touchy point here. If you make this too big, you cut the swirl. If you have it too small, what happens is the gas speeds here are high, and they come up here and they prevent this stream from A, entering the cylinder as easy, and B, swirling. So too big or too small, and you pay a price, right? Either in flow or swirl or both. Right, so that's the one to use for that. On this side, I used this ball wheel, but I finished it off with this 3/4 inch emery thing. So I made it as wide as I needed to and then finished it off with those. The rest of the port I did with this 1/2 inch, with a 1/2 inch 60 grit emery roll. Right, so that does it for the down the bore of the intake, or down in the bowl. Let's take a look at where the air goes in. So what am I doing here? I'm using this flow ball to check to see where the flow is going. Now, basically no metal has been removed from down here. And the interesting thing is, if we put the ball in here, it makes no difference to the flow. So basically this part of the port's redundant. On the other hand, where I spent the time on doing the radius at the top of the port here, getting this wall here with a nice curve on it, if I get the ball at a certain position, the flow drops 25, 30 CFM. So that's a busy area, so that's the place we need to work there. But I don't think we can take much more out of that. But anyway, let's take a look at what we've done and then take a look at the results. What I want you to see is where I placed the flow ball when doing that test just now. Here on the roof of the port, this here is a critical area. This radius needs to be as smooth and generous as possible, right? And you can actually widen it as well. You can't go too far here. This is the pushrod pinch, and this has been widened to within 50 thousandths of the pushrod hole. A little bit of metal has been taken off on this side to get the area across here as large as conveniently possible and functionally possible, but almost nothing has been taken off here other than just to smooth it out. Right, so that's what we have for the throat there. The actual area here has only increased very marginally. All the work on the port resulted in about an 8 cc gain in port volume, so not big. Here's a shot looking down the exhaust port. What I've done here is take this wall down so that it's moved much nearer the cylinder wall, which is of course here, because the flow is going to be going out the cylinder about like this. So we need to give it room here. It has a tendency to want more room this side than on the other side. That doesn't mean we ignore that, but basically we do the other side around here, the top side with that 1/2 inch ball, but we do this here. We can do that with a 1/2 inch ball, but we need to make it wider, right, here, and finish it off with one of those 3/4 inch emery rolls that I've just showed you. Right, now coming off the seat here, we can skinny down the width of this radius and get that round, because once it gets past a certain point, it has very little effect on the flow. We don't want too much flow going out this side, because it'll shoot across the port that way, and it will jam up the flow that wants to come this way, which is the preferred method of going out. Here is our CD curve, and you can see the form that the exhaust is taking. Notice how it's climbing very steeply after the lift gets past 0.25D. Here, the intake still is not climbing, but we'll give that some attention and see if we can fix that. Now, we took about 8 cc's out of the port to get to this, so let's have a look and see what our port velocity looks like. Well, here we are, port velocity. We are sitting right on the 300 feet per second speed for the intake, and we are exceeding it at 700 on the exhaust, but we really need to have a little bit more speed in around here, so it's about 280. So maybe some work on the exhaust seat will help that, especially as it needs to get from the quench side into the port easier than we're allowing it with the pretty roughed up seat job that we've got currently existing on the head. Well, I've just done a finishing cut on the chamber we're working on, so let's take a look at that. Did that with my 3D Goodson cutter setup, which is done right. It's almost as good as a Surdy. Here is the test cylinder or test chamber seat cut. I used 3D pilot and guide like this. This is my bowl cutter. You see the form on that cutter there? It very closely matches that. So I'm going to try a cylinder over here using this because it will be much quicker and more consistent. Anyway, seat details. Looking down on the seat, 50 thousandths wide. That's looking down this way. Looking at the seat across its width, that's 71 thousandths, right? That's Pythagoras' theorem to work that out. Anyway, a few points on this. Any less than 50 thousandths on the bore, on the inside diameter compared with the outside diameter, you'll lose flow. Any less, you'll lose flow. This is the optimum size and it works very well for street or race. The OD of the guide, let me get a caliper here. I don't know if you can see this because it will be upside down, but the seat is about 3 thousandths wider. About 3 thousandths wider than the valve OD. I like to cut them like that because it just seems to hang on a little bit better on the flow, and it flows slightly worse in reverse. Very small, but that's it. The best thing is about 3 thousandths to 5 thousandths bigger than the valve. Okay, I think that's it. Let's just get the cleanup done on that seat and we'll retest our cylinders. Seat's cut and the chamber finished off. But before I loaded it all onto the flow bench, what I wanted to do was to show some details. First, if you look very carefully, you'll see there's a witness mark here. That's part of the original casting, right? It's not poor workmanship, not polishing it out. This area here, just here, you need to try and not take any metal at all off because it doesn't increase flow, it decreases it. We don't want air coming around there and out there. This could be part of the reason the port is getting shut off at high lift. The seat itself is cut and I've polished it. Now I've got a technique I teach my students here, how to polish a seat with a tool that I've got, which takes off edges but has almost no effect on flat surfaces like the seats. Done on both valves here, right? The chamber's polished because that prevents stuff sticking to it as easy. Now, this area here, if you look at the pen reflection, you'll see that it's curved. This here curves it, this surface here curves into that one. Flattening this out like this is very important. This is 6 or 7 top end horsepower and no loss of torque anywhere in the power curve. Ports, seats polished on this, so that's good, and these are all area ruled. Oh, one aspect that I didn't mention is, and you'll be hard pushed to see this, but the roll into this turn here, the radius here and here, that's from this segment right round to about here, is a bigger radius than this one. So the actual hole in the beneath the valve is shifted that way so that we get a bigger radius here where most of the air is flowing, and we try and cut the airflow here so that it doesn't come out, turn this way and affect the air trying to turn that way. Right. It is now flow bench time. Yeah, that flow testing looked good. Let me just score it and then we're done. As you can see, we've cracked the 200 CFM mark on the exhaust, and we've passed the 260 on the intake. It's not too bad a number for still what is a small port. Now, my son-in-law, who is a NASCAR engine builder and head porter, he's done a lot of pro stock stuff, and I believe he did Jimmy Johnson's engine when he won the Busch Championship. But anyway, he's got a benchmark which I think is very relevant on the exhaust. If you've done the exhaust well, you should be able to crack the 200 CFM at 500 lift. A proviso with that though. I think that's more in line with a port that's been slightly raised rather than the stock position of the Edelbrock port here. But we're getting close. Here's the CFM of flow test prior to the one we're looking at now and our current one. As you can see, pretty big gain in the exhaust here. But we've kind of developed a dip there. I don't know really what that is at the moment. Probably some little disturbance in the exhaust. But on the intake, you can see that we're starting to conquer that leveling out at the top here. Right, so that's good. Now let's have a look at our discharge coefficient. Here's our discharge coefficient. You can see we've made a huge gain in the efficiency at low lift. That's all seat work, right? But as the lift goes up, so the two lines get closer, so the efficiency isn't up very much. But now we're starting to get an upturn on this. We've got a great upturn on the exhaust, and so that's working out good. But we need to check to see if this has come at the expense of any velocity. So let's look at velocity now, and there's the velocity. What we've done is we've increased the efficiency to a greater extent than we've increased the port volume. So not only do we have more flow, as shown by these two thick lines here, than the previous test, but we have more velocity, and that translates into more port energy. We've gone up with port energy, and we've gone up on the intake, and we've gone up this much on the exhaust. This is all good. It improves the ramming efficiency and the lower speed tractability, especially when you've done it on the exhaust. Right, let's do our next test where we go in and detail out the ports. That is the finished finish on there, the final finish. Doing the lighting for some of this finished porting work can be a little difficult. It's out of screen at the moment, but I'm holding lights all over the place because I just don't have enough stands for it. Anyway, there you can see what a finished port and ports and chambers look like. However, just visualizing it like this is not going to tell you very much. So what I'm going to do is take a mold of these ports, and you'll be able to see what's done far easier. Here's an intake port mold. Points to watch are this here. We can't get much more of a curve in here, not much metal has come off here, so this form here is not what I would call optimum, but it's what we're stuck with if we can only remove metal. Now, note this turn here. This is a big radius here and less of one there. Now let's just rotate the port so that we can see it end on with the bias. If you look carefully in this shot, you'll see how the port leans like this. The air comes in like this and goes out through the center of the cylinder. Note that this area here is cut away more than this area here. In spite of the fact we've taken a mold, it's still difficult to see, but this turn here is critical. The radius on this wall here needs to be as large and as smooth as possible. You do not need to widen the port at the bottom here. All of the air is flowing, I say all of it, the majority of the air is flowing above about that line of my screwdriver there. This is a busy area right down through there, and so is that. That's where you should focus your attention. Do not widen the bottom of the port here, this is the floor, any more than you have to. Another point to note is the short turn radius. Notice how it turns the sharpest by the seat, and the radius gets bigger and bigger as we go around. By comparison with the intake, the exhaust is pretty easy to do. First off, notice how there's more metal off out to let the exhaust, it comes out the cylinder like this and out. So there's more metal off this side, and you can see it leans. Right, that's the bias on it. Like the intake, the short side turn is critical, right? Starts sharp there and then comes out to a bigger radius. This wall here, the short side, the long side turn is almost stock. I'm not too happy with this straight up design, but that's what we've got. There's almost no material off here. So don't take any more than you have to. Well, that was the last of the flow tests on the final detailed port. And it's looking good. So let's just check our results here. Here's our final figures. We're over the 200 mark by a respectable amount on the exhaust, and we are just shy of 270 up here. I did check at 50 thousandths light higher lift. Still didn't make 270, it just leveled out at about 269. That's all looking good. Now then, next move, just for a case of reference, let's have a look at our efficiency curves. Look at this. This is why we're doing so well here. Efficiency of everything has gone up a bunch. Right, now let's look at the mean port velocity before and after. And what we have here is all that extra flow, plus we are over the magic 300 feet per second at the valve lift we're going to use. I think we're about 306 on both intake and exhaust. So we've scored well on that. Now let's have a look at the port energy. Right, calculate, graph. Port energy, we are way up on the stock one. So that's a winner there. Right, now let's have a look at the port energy density. Right, this is going to require a quick explanation here. The port energy density is something I teach my students. What it does is it allows you to grade the effectiveness of the cylinder head, because it removes the size of the port and the diameter of the valve from the equation. In other words, it's like this is the specific energy, port energy, right? So it's measured in port energy density, foot-pounds of energy per square inch per foot length of port, right? We are in the very good territory here, right? A really good cylinder head is around the 26 on up. Formula One stuff's usually around about 34. Pro stock, 29 to 30. So we're doing well there, very well. But our next move is to see what this is going to produce in terms of power. We have 1.98 square inches. We have 255 CFM at our lift. And what that gives us for our engine is Peak torque of 531 foot-pounds. Peak power 516 plus. It'll be a bit over that. So we've achieved the horsepower goals, but that's not all. Let's now look at the RPM at which peak power will occur. Right, that will be peak power target RPM was 5,800. Program says 5,799. I think that's close enough. Here's the finished product as far as one cylinder goes. Anyway, let me just say that the work we've put into this has paid off, because we've potentially gained something like 70 horsepower over the stock head in a street configuration. Right, not too shabby if you know what you're doing here as a gain from porting. Let me make a point here on the horsepower business, right, and the torque. Those numbers that the program presents are making the assumption that the engine builder knows what he's doing. In other words, he's putting together a bottom end that doesn't have excess friction in it. It's got a good piston and ring selection, right? The camshaft matches the cylinder head, and I'm talking about a proper match here. You've only got, it doesn't matter how good your cylinder head is, if the rest of the stuff doesn't, what's the word I'm looking for, complement it, then it's all a waste of time. Now, building combinations is not something that magazines do articles on very often, but my 3-day seminars, how to build horsepower seminars, that's the focus there. How to build a working combination, what effect one component has on another. This cylinder head here is going to deliver those power figures if the cam is right, the intake's right, the carburetor is the right size, the exhaust is the right size, etc., etc. Those are very doable numbers. In fact, professional engine builders almost always exceed the numbers I give in this program. That's because I give the average Joe Blow a little bit of leeway. So what are the conclusions we can draw from this review of the Edelbrock heads? Well, at a price of around about 870 odd bucks, they look to be a pretty good deal. They have good hardware, etc., etc., and it's a good entry-level head. But I have to say that the import heads are catching up. Although the Edelbrock head is still a good head to rework, like I've shown here, right, what we do need to consider is that there are some viable options out there from the offshore producers. Now, I don't like to recommend them just carte blanche, because I've had some terrible offshore heads, but they're getting better and better. And I think the bottom line is Edelbrock have a good head, but they need to be looking at updating that cylinder head. Just a few minor details will put them one step in front of the people they're competing against. They can't compete on price, so they've got to compete on performance. They don't have an option. Before I go, I'd like to say that if whatever you saw in this video was something that you'd like to see in lots of other subsequent videos, then please hit that like button and the subscribe button. When we do dyno testing, it's not cheap. It's between $500 and $650 a day. And I'm doing this stuff for you guys out there. So if you want to see a continuation of this real speed tech, then you need to like and subscribe. Thank you.